Welcome everyone to our new room, which is about 3 times as big, and hopefully it'll make a lot of the AV stuff easier as well. Also very convenient for me because my office is on the 7th floor. Hans-Peter and Verena will still have to walk over here. So, you know, it's not my fault that the Science Center has bigger rooms than Northwest or Maxwell Dorkin. So, couple announcements. Actually, homework 1 is due next Thursday. Sorry to. This should say next, so don't panic. It's not due today. It's due in a week at 11:59 p.m. But you should start last week. If you haven't started yet, go back in time and start last week. Because the homework is long. It looks very long. It's not as long as it looks because a lot of it is expository, but you have to take the time to actually read and understand the expository stuff. And it's still long, so you definitely do not want to procrastinate on that. Section assignments should be coming very soon. So starting next week, you should be going, for the local students, you should be going to your regular section. You'll get more information from Rahul about that soon. And just a couple Piazza etiquette pieces. There have been a lot of duplicate questions, which makes it harder to find what you're looking for. So always try to do a search first and not post the same question that's already been asked. And you know, if you're asking a question that's similar to previous ones, it may help to at least show that you've searched and say, you know, it has the at notation like @7 or question, you know, post 7, and kind of refer to how your question is different from the other ones there. I already scared 2 people off. We didn't get into anything hard yet. And check out Andrew's post. Andrew's one of the TS who had a helpful post about, again, Piazza etiquette and rules about not posting code and things like that. So today's a kind of a tricky, this is just a quote I really like, except I don't know who first said this quote, so I don't know how to attribute it. I attributed the picture from where I took the picture. Someone said, "We're drowning in data but starved for information." So this is, of course, in data science, not big data per se, although we will be getting into a lot of big data stuff as well. Big data doesn't necessarily mean big amount of information. Sometimes it means big amounts of noise and big amounts of confusion. And so, you know, the general theme that we'll come back to over and over again is how do we deal with this deluge of data and try to get useful insights and information out of it. And one important strategy for that is to use statistical modeling. So today is really about some basic stuff about statistical models, some of the most famous models and methods in statistics. Kind of a challenging lecture to give because some of you have had Stat 110, which is my probability course, but haven't studied and haven't taken applied statistics, haven't taken statistical inference, and some of you have taken a course like Stat 100 or 104 or, you know, Intro to Applied Statistics, but not so much probability. So you know, we have an extremely large class, and you have many, many different backgrounds. So we're going to be posting additional resources and readings and things like that. But it's kind of tricky to, you know, there's a risk of confusing everyone if I go one way or boring everyone if I go another way. Hopefully I try to keep everyone interested and not too confused. But you know, keep in mind that there's so many different backgrounds here. So I want to, at least for today, get everyone to a certain basic level of knowledge about the most important probability distributions that we'll need, and a few statistical models that we'll need, and statistical methods. But first, actually, what is a statistical model? Because if you never studied, you know, the word model is used all the time informally, but what does it actually mean in statistics? I'm assuming you're familiar with a probability distribution, and we'll review some of the most famous distributions. So in a probability course like Stat 110, we generally work with one distribution at a time, right? Like we might work with a standard normal distribution, or a Poisson with parameter 5, which we'll be reviewing the Poisson in normal later today. So we're working with one distribution at a time. In practice, though, nature never comes up to you and says, my parameter is 5, right? So we have the scientific challenge of figuring out what the parameters are. That's called statistical inference. So statistical inference is the direction of you have some data, Well, that's something we're going to be encountering a lot. It's a data science class. So you have some data. You want to learn about the world, learn about the science. You need to estimate the unknowns, right? So that involves both estimating unknown parameters and making predictions about the future. So a statistical model means you don't just have one distribution, you have a family of distributions. For example, you could say, well, I think my data have a normal distribution, but I don't know the mean and I don't know the variance. So there's two parameters, the mean and the variance. And we want to estimate those. That's what statistical inference is all about. And, what if you, why do you want to do that? Well, first of all, in many cases, those parameters themselves are of scientific interest. That it has some scientific interpretation. You want to learn about it. So we try to estimate it as best we can from the data. In some problems, though, those parameters in your model, you don't actually care that much about them directly. They're just a tool, okay? Because if you can estimate the parameters of the model, you can use that to make predictions about future data. And so whether or not you actually directly care about those parameters, they're a useful device for generating predictions. So a model is a family of distributions, and formalizing that is actually one of the biggest breakthroughs. Statistics is a young field, and one of the big breakthroughs around, only about 100 years ago, this was due to R.A. Fisher, who was arguably the greatest statistician of all time. I think it was in 1920s, so, less than 100 years ago, he formally wrote down, here's what a statistical model is, here's the parameters, here's the data. And before that, people were working with data. They didn't have the kinds of massive data we have now, but they were collecting data. They were working with data in the 1800s as well. But if you look at what they were doing then, there was all kinds of confusion between, what are you trying to estimate, right? Like the true unknown parameter of nature versus your estimator. Estimator, I'm saying for emphasis. Normally we just say estimator. Your estimator is what you calculate from the data. Okay, so you use your data to generate an estimator. You use that to estimate the unknown. So it's having this sharp distinction between the unknown parameters, which are the true way that nature behaves, at least in your model, and your estimates of those things. That clarified a lot of mistakes because it's so easy to make mistakes in statistics, and there were even more mistakes before that distinction was really made. And we're interested in both parametric models and nonparametric. Nonparametric is actually kind of a misnomer. A parametric model is something like a normal distribution or a Poisson distribution, which we'll be reviewing, where there's a fairly small number of parameters, like the mean and the variance, and those are your unknown parameters. Nonparametric sounds like there's no parameters, but actually it means it's an infinite number of parameters. It's an infinite dimensional space. And so there are a lot of arguments about should you do something parametric or should you be nonparametric. Some people will say nonparametric is better because it's more general. That, like, why are you assuming a normal distribution or something like that when you know the data are not really normal? But another important principle in statistics is that there's no free lunch. So it doesn't make sense to say parametric is always better or nonparametric is always better. Nonparametric has fewer assumptions about what specific distribution the data take, but that always comes at a cost, right? Because you're doing something that's so general, which seems nice, but then you might actually need a huge amount of data to actually estimate it well. So you know that the data are not exactly normal, but if they're approximately normal, like if it's a decent approximation, you're going to do a lot better probably using that approximation than just trying to do something that's completely general. But even with massive data sets, it's still not necessarily going to be enough for the nonparametric methods to work. So there's pros and cons. There's always trade-offs in statistics. So that's another principle. No free lunch. Everything's a trade-off. Okay. So we'll be considering some parametric methods as well as some nonparametric methods. Nonparametric, the most famous types of nonparametric methods are Bootstrap, which we'll talk about later today, and kernel density estimation, KDE, which we'll talk about in a later lecture. Okay, so that's the definition of a model. Why do we want a model? This is maybe one of the most famous sayings in statistics. All models are wrong, but some models are useful. This was stated by George Box, who was one of the greatest statisticians of recent years. And, okay, if the models are wrong, how might they still be useful? Well, the point is simplicity. And the real world is too complicated, so we need a model. We know the model is going to be wrong, but hopefully it will capture something. So there's some kind of signal mixed in with all the noise, and we're hoping to capture it. This was a nice essay from Bohr Hess. It's about these expert map makers, and they were making better and better maps of the world. That was the Bohr Hess Google Doodle from a while ago. You can actually, if you read Bohr Hess's short stories, you can actually find a lot of analogies with big data in there. So these map makers were getting more and more precise and making better and better maps, but to make a better and better map takes up more and more space and more resources. Right? So they kept building better maps and better maps until eventually they had a map of the entire empire that was so detailed that it was the size of the empire, and it coincided point for point with it. So that's useless, right? So the model has to be a simplification, otherwise it will not be useful. This was a parable I found. It's called big data versus pig data. The link is there. We'll post the slides after class, and you can read the parable. I recommend it. It's one of the best kind of like short story parable type things I've found for why we still need models in this age of big data. Because there have been some recent articles. There was a notable one in Wired that I was going to link to and quote from, but it's so ridiculously wrong, I didn't even want to publicize it more by putting the link there. But there have been several articles recently that basically are saying, you know, we're in this amazing age of big data, which I agree with, and then go into to say, and because we have this big data, we can just develop an algorithm, run it, and let the computer figure everything out. We don't need to specify a model. We don't need parametric distributions anymore because we have you know, unlimited amount of data, and then you know, you don't need models anymore. And I think that's completely wrong-headed. And this pig story explained it really well. So I'm just going to say it briefly, but you should read that story. But it's about some pigs. You see that one saying, "I hate models." So they have massive amounts of data, and they're trying to use it to make predictions about everything. And in particular, they're studying gravity. Okay, they don't know about Newton's laws and things like that. Okay, they just they try dropping different objects, making lots of measurements, which is all great, right? That's empirical science. You drop a feather, drop a bowling ball, and they see the bowling ball drops faster. Come up with big, complicated models with many parameters for, predicting the rate of fall of different objects. And eventually they're able to make predictions pretty well. But they have no insights, right? With their approach, they're never going to figure out Newton's laws. They're never going to figure out, that the objects would fall with the same acceleration in a vacuum. They have no scientific insight. All they're doing is making predictions. They're building a black box. And it doesn't work out too well for them. So you can read that. There are lots of books on statistical modeling. You could easily have a full year course just on models, and so we're limited in what we can do in one lecture. Here's two books I recommend on statistical models. They're both called Statistical Models. One is by Davison, and one is by Friedman, both great statisticians. The funny thing is the two books have the same title, and I've read both of them, and I like both of them, but there's actually very little overlap. The two books could hardly be more different. The main overlap is linear and logistic regression, which are topics that we're going to be doing in the next couple of lectures. So they both believe regression is important, otherwise they basically don't agree on anything. And what that really means is, you know, statistics is not just a branch of math. You need math for statistics, and you need computing. And of course, like this, you know, the computing and stat come together. But you also need to, you know, use some common sense. You need, it's an art, not just a science. You need to just kind of think critically, think scientifically, and think creatively, and think about stories and things like that. And there is almost never going to be one best model or one best method that just says, you know, where it's just screaming out that you have to use this method, right? There are many different methods. There are many different models. And so you want to be familiar with a broad range of different models and methods, and you don't want to be dogmatic about it and get into some, you know, we're going to be talking at some point about Bayesians versus frequentists. You don't want to get into all these holy wars. You want to be familiar with both Bayesian methods and frequentist methods, and we will come to both of them, you know, later on this semester. You want to be familiar with both parametric and non-parametric, and just know what's out there. And then when you're faced with a real problem, you're not being a dogmatist about it. You're trying out different things. You have an arsenal, you try different things, and then you try to actually do something sensible with it. And my other favorite statistics quote is from Sir David R. Cox. He said, there are no routine statistical questions, only questionable statistical routines. So when you're faced with a real problem, real problems, as we see over and over again in this class, they're messy and they're hard, and there is rarely a clear right way forward. You have to try different things. You can't expect that you can just pull one standard method off the shelf, use it, and it's going to answer everything for you. There's always going to be problems, right? Problems with the data and issues where the data don't exactly satisfy the assumptions, right? Because every method has assumptions. Even non-parametric, you know, claims to be extremely general, and it is more general than parametric in some ways, but there's still assumptions. You know, there might be independence assumptions, and maybe your data are correlated, right? There's always some assumptions behind the methods. And so it's rare that the assumptions are really satisfied, and you have to use some judgment and some kind of other forms of reasoning to try to figure out what's a reasonable conclusion. And if you can attack the same problem in multiple ways, that's so much better, right? Because if you get the same result from different approaches with different assumptions, then you'd have a lot more confidence in those results. And if you're getting very different results when you try different methods, I mean, it forces you to think harder about the assumptions and, you know, think harder about the data. So it's rarely a good idea to just say, oh, I'm just going to use this method, do the method, and then that's the end. You know, you want to do some checking and really thinking hard about the data. Okay, so I already talked about this distinction between parametric and non-parametric. But I was going to mention that, so surprisingly, that there is something intermediate between parametric and non-parametric, which sounds like a contradiction because I said parametric is finite dimensional and non-parametric is infinite dimensional. The dimension just means the number of parameters in your model. Okay, so a three-dimensional model means you have 3 parameters. How could there be anything between finite and infinite? Well, actually, there is something called semi-parametric as well. There's nothing actually between finite and infinite. So semi-parametric means you actually do have an infinite dimensional parameter space, but you can split it into 2 components. There's a parametric piece that you're interested in, and this non-parametric part, which is what's called a nuisance parameter. And sometimes we'll encounter nuisance parameters where a nuisance parameter means you have these parameters in your model that are not actually the parameters of interest. You don't actually care about it. But it's there in the model because that's just part of your model. And so there are some very, very clever ways for trying to eliminate the nuisance parameters and focus on the parameters you're interested in. So actually there is some middle ground there. And then I wanted to, again, going back to this parametric versus non-parametric question. So some advocates of non-parametric methods say, well, how would you even know whether your data look normal? Well, plot the data. So that goes back to a theme, you know, that will recur over and over in this case about doing some exploratory data analysis, do some plots, look at the data. All right, that's not a crime to look at the data. So, if the data don't look normal, then there are a variety of other models we can try, or we can transform the data. We might be able to do different transformations or manipulations and get it to look more normal or to whatever we want. So there's a lot of scope for playing around and exploring the data, get a feel for it, try to think about what distribution would be reasonable. And if you can do a parametric model that fits reasonably well, it will usually be more efficient. Okay, so for example, here's a famous distribution. So I want to review a few of the most famous and most important statistical distributions. I'm not going to try to cover all of Stat 110 in one lecture, so you should take Stat 110 for much more detail about all these distributions and how they're all connected. But just some brief familiarity with a few of them that you will need for this course. This is the exponential distribution. So its density function, f of x equals lambda e to the minus lambda x. That lambda there is called the parameter. It's called the rate parameter specifically because the interpretation of it is as a rate at which events occur. So, for example, if you use this distribution for, let's say I want to look at the rate at which emails arrive in my inbox. And, one model for that would say that the time from one email to the next one has an exponential distribution, okay? And then lambda would be, as a rate, it's the average number of emails per unit time that arrive, okay? So that's the density. What that means, I'm assuming most of you or all of you have seen densities at one point or another. It's an exponential decay, as you can see there. That's why it's called an exponential distribution. And what does it actually mean? In case you're rusty on this, what does it mean to say this is the density? The density is not a probability. In particular, a density could be greater than 1. A probability is always between 0 and 1. But a density is what you integrate to get the probability. So if I want to know what's the probability, if x is a random variable that has this distribution, and I want to know what's the probability that x is between 3 and 7, then I just integrate the density from 3 to 7. Any question you ask about this distribution, any probability you want to calculate, all you have to do is integrate the density. And in some cases, it's not hard to just do that integral by hand, assuming you've done at least basic calculus. Like this is a really easy one to integrate because it's just e to a power. For some distributions, that integral is extremely hard or intractable, but in that case, there are really good ways to simulate and approximate it using a computer and using Monte Carlo methods that we'll get into later on. Okay, so to get from density to probability, we just integrate. The plot on the right is what's called the CDF, cumulative distribution function. Again, I'm assuming you've seen them at some point, but just wanted to mention you should know what a CDF is. Notice the CDF is increasing. It's the probability of the random variable being less than or equal to some value, and you increase that value, and so this will increase smoothly from 0 up to 1, approaching 1. Okay, so in other words, if you integrate the PDF from minus infinity up to x, that's going to be the CDF at x. It means as you're integrating, you're looking at area under the curve, right? You're accumulating more and more area, and then that gives you the CDF. Okay, I said at the bottom, remember the memoryless property. The most important property of the exponential distribution is that it's memoryless. What that means is, if you're thinking of it as a waiting time, that let's say you're using an exponential distribution to model how long is it going to take to do homework 1. Suppose that's modeled by an exponential distribution. What that means is no matter how much time you spent on it, if you haven't finished the homework by then, and then you're looking at the additional amount of time, it's still a fresh exponential distribution with that same parameter. So I actually hope that's not the case for homework 1, okay? hopefully it's something where, you know, you're working on it, and as you're working, you're improving your Python skills, you're getting better and better at understanding what's going on. It's very expository, and then you're making progress, okay? The exponential will be something where you just like stare at it blankly for hours and make no progress, okay? Hoping you'll make a lot of progress. So that's what the memoryless property means. Okay, so exponential is actually not a good distribution to use for time it takes to do a homework. It might be good for like time it'll take to solve the Riemann hypothesis, or you know, some unsolved open problem in math where someone might solve it tomorrow, but it might take 300 years and maybe still no one will have solved it. It's not clear how to even measure progress in a problem like that. Okay? For human lifetimes, exponential, sadly, is not a good distribution to use. It's saying there's no wear and tear. You don't really get older. I mean, you get older, but you know, you don't have signs of aging, right? So if the life expectancy of a human being is, say, 80, and if you're 40, and if the exponential distribution holds, then your average life expectancy would be 120, because you still have 80 years left on average. Okay? So that's a very bad distribution to use for human lifetimes or animal lifetimes, but it's a very good distribution to use in various problems in chemistry and physics, and it all depends on the problem. Okay? So the memoryless property characterizes the exponential distribution. What that means is that this is the only continuous distribution that has the memoryless property. So that actually tells you a lot. It tells you that if you want to have the memoryless property hold for your problem, you have no choice but to use the exponential. It tells you what to use. Okay? Well, what if you don't want the memoryless property? What if you don't know whether the memoryless property is reasonable in your problem or not? Well, again, look at the data, right? So plot the data, you can compare it with an exponential, and all models are wrong, but some models are useful. So even if the exponential is a very crude approximation, at least it gives you a baseline, right? At least it gives you something to compare with, okay? So you know, if your data do not fit an exponential, then you can actually learn something useful by saying, you know, can you describe the discrepancies, right? In what way is it like an exponential? In what way is it not like an exponential? So, you know, describe the differences, and then iterate. Remember the data science process? Everything is iterative, okay? We iterate between exploration and getting data and modeling data and communicating. Everything was iterative. Everything was interconnected, okay? So exponential would be a very simple starting point as a toy model for something like, you know, the time from one email to the next one. Not very realistic. And then we look at the real data, compare, and then see, okay, can you do better? So models, you know, are model fitting, model building, it's all an iterative process. This is the Weibull. The Weibull is obtained if you take an exponential random variable and raise it to a power. That's called a Weibull. For example, take an exponential random variable and cube it. I'm pointing at, you probably don't need to use Weibull in this class, although it could be useful on the final project. Probably won't be needed on the homework. But I wanted to talk about it right now because, first of all, the Weibull is the single most widely used distribution in survival analysis. So for the types of problems I was talking about, like, you know, model how long will a human being who has a certain disease live, or things like that, the most common distribution that's used in biostatistics and epidemiology is the Weibull. And my point is that the Weibull, where did the Weibull come from? It's just a transformation of an exponential. So like, memoryless property is not realistic for human beings, but it turns out if you raise it to a power, it's a very simple modification. It's no longer memoryless. It's a much more flexible family. It has an extra parameter, right? Because for the exponential, we just had one parameter, lambda. For the Weibull, we also have a parameter, which is the power you're raising it to. The more parameters you have, the more flexible that family is to try to fit different data sets. And so the Weibull's not as famous as exponential, and yet even the Weibull has a huge literature. That book I showed in the picture there, that's an 800 book just about applications of the Weibull. Okay, so if you look up the definition of the Weibull on Wikipedia or something like that, it's going to be this weird-looking density. And you might wonder, where did that density come from? So I wanted to emphasize that the best way to think of the Weibull is relating it back to the exponential. So think of the exponential as your building block. So even though exponential itself is a very crude, simple model, still very useful in physics and chemistry, but not so much for human beings, but you can modify it and get much more flexible, much more realistic models. And if that's still not realistic enough to use a Weibull, then you can make it, again, iterate, make a bigger model, and can continue that process. So I'm not going to talk about all these distributions today. This is, these are distributions, the most important distributions that we talk about in Stat 110, but we don't need all of them here, at least not today. But I just want to illustrate that they are all connected. Some probability courses would give you the impression that you just have, a list of famous distributions, and they're all given by their densities, and you memorize all of them, and that's it, okay? But actually, they're all connected in different ways. Under some conditions, one is an approximation for another one, as you take limits and you get from one thing to another. They're connected through certain processes, like if you're imagining, emails arriving in an inbox or cars that are passing by a certain point. You may use a stochastic process to model them that would connect Poissons and exponentials. That would be called a Poisson process. They're connected by conditioning. So if you do conditional probabilities of, for one random variable given another one, you can get between them. So I'm not going to explain this whole picture. I just want to illustrate that they're all connected. Okay. All right, so here's a quick review of the binomial. I'm assuming you've seen the binomial before, but just to make sure that you all think about it in the simplest way. The nicest way to think of the binomial is not to write down the formula for it, it's to think about what it means, what we call the story. Story for the binomial is that we have n independent trials. Simplest example would just be flipping a coin, but it could be, you could think of the voters in an election as the different trials, and, are they going to vote for candidate A or candidate B? And if you assume those voters are independent, and let P be the probability of voting for candidate A, and 1 minus P be the probability of voting for candidate B, if it's a two-party election, then the number of votes for A is going to be a binomial, okay? So it's counting the number of successes in n trials, and you can define success and failure however you want. The key assumption there is that those trials are independent. So again, it's a simple model. This would be the case if those voters are not influencing each other. Things get a lot more complicated if you imagine that those voters, form some kind of social network, and they're talking to each other, and they're influencing each other, and debating with each other, and things like that, and you have correlations. Or, you have different states in the US, and in different states, voters behave differently. So here I just have one parameter n and one parameter p. N is the number of voters, or the number of coin flips, or the number of trials, and p is the probability of success. Okay? Much more realistically, different people have different probability of voting for the different candidates, and those probabilities, you could estimate in terms of whatever information you have about those people, age, income, religion, whatever you know about those people, and you could estimate those probabilities. But again, it helps to have a simple model to start with, and then you could develop more sophisticated models that incorporate whatever information you have. Okay, so it depends on what information you have about those people. More information you have, you can build more sophisticated models. Okay, so these are just the probability mass functions for some examples of binomial distributions, and you can change n and p to be whatever you want, and then this is just plotting the probability of equaling that value. So of course, a binomial with n equals 10, it's always going to take values between 0 and 10, counting the number of successes in 10 trials. Okay, so that's the best way to think of a binomial is that it's really a sum of independent Bernoullis. Bernoulli is binomial with n equals 1. Bernoulli means you're doing one coin flip, or one voter, or one experiment, okay? And then to get the binomial, you're adding up across all of those trials. So, for example, we can see that, so important E stands for expectation. That's just the average. Very important property of expectation, which hopefully you've seen, but in case not, make sure I'm mentioning it now, is linearity. Linearity of expectation says that the expected value of x plus y is always the expected value of x plus the expected value of y. That's always, always true for any random variables you could ever come up with. It doesn't matter if they're independent or not. That's called linearity. So in particular, it's not hard to show, once you're familiar with the definition of the average value of a random variable, it's just an easy calculation to show that a Bernoulli has expected value p. So from this, you can immediately say what the expected value of a binomial NP is. It's just n times p, because you're just adding up by linearity, right? You're adding up p n times, so it's np. So once you're comfortable with linearity, you can do things like this in your head. Whereas if you try to do kind of like brute force ways that a lot of books emphasize, then you have to do a big calculation, do a big summation, do a lot of algebra, and eventually you get NP. Similarly for the variance, so I'm assuming everyone has at least seen standard deviation before, in intro stat. The variance is defined as the square of the standard deviation, or vice versa. Standard deviation is the square root of variance. And that's the standard measure of how spread out a distribution is. The mean is a measure of the center, and standard deviation is the measure of the spread. Okay, well, you can calculate that for a Bernoulli, the variance is p times 1 minus p. And a useful fact from Stat 110 is that if you add up independent random variables, the variance is just add. So it follows immediately that a binomial has variance np 1 minus p. Again, you don't want to do a calculation there. This actually came up in Doonesbury. Doonesbury is a famous political cartoon. And normally it's dealing with all kinds of political controversies and things like that. So I was very shocked one day to find them talking about the binomial distribution in Doonesbury. And you can see, I don't know if you can read the words here, but you can see that there's this professor who's writing on the board, and he says, which is how we can determine the variance for the binomial distribution. Pretty great, right? Anyone see that coming? The validity of this proposition is thus confirmed in a most elegant fashion. Now, as you can see, this is a very complicated proof. But then it's very sad because most of the class is just on Facebook and texting and things like that, and the professor seems kind of bitter about the whole thing because it's hard these days to get students to actually pay attention. So I did feel sympathetic for this professor, but I also thought that, it's a two-way street, right? If you're doing it that way, that's just boring, okay? That is not how you should get the variance of the binomial. The way to get it is what I just said with the story, okay? The story is the elegant way. He's doing some ugly math there. So then I was less sympathetic. All right. Poisson. Yeah, and I'm hoping you've heard of the Poisson before, but I'm not sure if everyone has because we list Stat 100 as the prerequisite, and Stat 100 mostly does normal and binomial, and I don't really think they get into Poissons. Poisson is arguably the single most important discrete distribution. Continuous distributions means it can take any value in some interval, like any positive real number. Discrete normally means it's integer valued, okay, some specific list of numbers that it could be. So Poisson is for counting. This is the single most widely used distribution in all of statistics, theory and application for modeling counts. You want to count something. Obviously, it's an integer because you're counting. Poisson is the most important distribution. So that's the formula for the PMF. The reason that adds up to 1 is just the Taylor series for e to the x. But where does that actually come from? Well, it turns out we're going to avoid proving theorems, okay? Because this is not meant to be a course where we're doing tons of math. We're emphasizing the statistics and CS aspects. But it turns out that, there's theorems. I will mention one theorem about this. I'm not going to try to prove it. Okay, there are theorems that basically say if you have a large number of events that are independent, so any one of those events may or may not occur, but all of those events are very, very unlikely individually, right? So imagine you have 1 million different events that could occur, but each one of them is extremely unlikely, and then you want to know how many of those events occur, then Poisson is going to be an excellent model for that. So for example, if you're counting, you want the distribution for the number of mutations, if you're working, with a DNA sequence, and you have, millions and millions of positions at which a mutation could occur, but, the process is very, transcription is very reliable, and so the chance of a mutation is very, very unlikely, but there's so many millions of ways it could happen, you're going to get some mutations, okay? What about number of traffic accidents? Well, imagine you're looking at a certain intersection, and, cars are passing by there a lot. Many different cars go by that could have an accident. Usually they don't, right? But if there's a lot of cars that keep coming and coming, there's going to be some accidents. So if you wanted to ask, how many accidents are going to occur at that intersection in a particular month, Poisson is going to be a very reasonable model for that. And I'm not saying it's exactly Poisson either. I'm saying that would be our starting point model. Then we should go and get some data, compare the Poisson with the data, and if Poisson is not good enough, then we can build a better model. But in many cases, the Poisson is already going to be an excellent model for that type of thing. Number of emails that I receive, in the next 3 hours or something like that. Well, I could think of it this way. There's billions of people on this planet, right? But any one person is very unlikely to email me in the next 3 hours, or at least most of those people are unlikely to email me in the next 3 hours. Some people email me a lot. So let me change that 3 hours to 1 minute. How many emails will I get in the next minute? Well, again, billions of people who might email me in the next minute, but it's unlikely for any one person. So Poisson would be a very reasonable distribution there. Okay? The parameter might change depending on the time of day, right? Certain times of day you're more likely to get emails than others, although time zones come into play too. But a very reasonable starting point would be a Poisson distribution for that type of thing. So just to have a few pictures, the top row is the Poisson of 2. Poisson has one parameter called lambda usually. The mean and the variance are both equal to lambda, which is very easy to remember. So Poisson of 2 has mean 2, which is why you can see that on the upper left it's basically centered at 2. And on the lower left it's centered at 5. That's a Poisson of 5. Those are the PMFs. CDF, cumulative, means on the right means you're accumulating probability. And the connection, you should all be familiar with the connection between a PMF and a CDF. The connection is, if you look at the two plots on the left, in each of those the total height of the bars, if you stacked all the bars up, the total height would be 1 by definition. The probability that it must take some value. The probability is 1 that it'll be something. So you imagine stacking up all those bars on the left. The CDF keeps jumping. It jumps every time you reach a new integer, and the heights of those jumps are the same as the heights of those bars. So you can go from the PMF to the CDF and back. Notice also that compared to the Poisson of 2, which is up above, the Poisson of 5 down there is more symmetrical. It's closer to normal looking. If you do Poisson of lambda and lambda is large, it's going to look like a bell curve or a normal distribution, which we'll review in a bit. Okay, I'm just going to state one theorem, just because this theorem is so general and so cool. Definitely not going to try to prove it. But I just wanted to point out that there is a very quantitative way to say how well will you do with a Poisson approximation. It's an amazingly general theorem. And what this says, just briefly, as I said, you're trying to count the number of events that occur. Let's call that X, right? So that could be number of mutations or number of emails or whatever count you're trying to model. And N is a Poisson. And the question is, how well will you do in approximating your count, which is x, and you want to approximate it with a Poisson, n. And this is just saying, look at the difference in the b here is any set of integers. So in other words, I'm asking any probability question. You know, what's the probability that the number of car accidents will be between 1 and 5? Then I would let that set B be 1, 2, 3, 4, 5. It's whatever question you're asking. It's saying that how far off your probability is from using the Poisson approximation is never going to be more than that thing on the right, where it's based on the sum of pj squareds. Pj is the probability of the jth event happening. Remember I said the pj's had to be rare, right? You're working with rare events, okay? So the cool thing here is that the pj's get squared. The pj's are small numbers, right? Otherwise this wouldn't work. I'm talking about rare events, okay? So you have a lot of small numbers, and then you're squaring them, okay? And so they get even smaller. You are adding them up, and so that's where there's this trade-off, right? Trade-offs everywhere. You're hoping there's a lot of events, but they're each rare. You're hoping they're very rare, okay? So you're hoping the pj's are very small, pj squared's even smaller, and then the right-hand side is telling you a bound on how far off you can be if you use the Poisson. Okay. So, quick example would be like the matching problem is a famous problem in probability. Just briefly, brief version of this. Suppose you had n envelopes and n letters, okay, and you're supposed to put, you know, each letter is addressed to a certain person, okay, and the envelopes are all addressed, and then usually this is phrased in terms of a deranged secretary. So you have a secretary who's really bitter, shuffles all the letters, and then puts them all into random envelopes, okay, instead of putting, you know, the correct letter into the correct envelope, okay? Then the question is, what's the probability that none of the envelopes will have the correct letter in there, okay? All right, so you can do a big calculation and do an exact answer for that, which we do in Stat 110. But just based on the things that I've mentioned so far today, just in this probability review, we can get a very accurate, very quick approximation, okay? Because the probability of one specific envelope having the correct letter is 1 over n. There's n of them, so by linearity, on average, one envelope will have the correct letter. And we're going to use a Poisson approximation because, again, we have a large number of, assume n is large number of envelopes. Each one is unlikely to have the correct letter, okay? So we have n different envelopes that could either do or do not have the correct letter, probably 1 over n for each of them. So the average number is 1, and we're going to use a Poisson of 1 approximation. The probability that a Poisson of 1 is 0 is e to the minus 1. So it's 1 over e. So once you've practiced Poisson approximation, this is just one example of many. Once you have some practice with Poisson approximations, you can derive very quick, very accurate approximations to many problems in probability and statistics where if you had to do the whole calculation explicitly, it would have been intractable. So it's a great way to get quick approximations. Okay. Here's a simple example of actually using Poisson to model count data. So I took this plot from a book by Peter Hoff, which is a really good book on Bayesian statistics, but it's public data about the number of children of a certain group of women based on a survey. And you know, these are a group of women in their 40s, I think, and the gray bars are the actual empirical distribution, that is from the data, how many children do these women have, okay? And then Poisson seems like a plausible model here for that kind of account data. And so how do you know which particular Poisson? Remember, Poisson is a model. A model is a family of distributions. So how do you know which particular Poisson to use? Well, luckily, the Poisson only has one parameter, lambda, okay? So an obvious thing to do would just be estimate from the data. So you have bunch of women in your data set and you know how many children each of those women has, an obvious thing to do, which is a pretty reasonable thing to do, would just be take the average and use that as your estimate of lambda, right? Because lambda is the mean of the Poisson, okay? And if you do that, you get the black histogram, which is what the Poisson model is saying. And you can see it's doing decently well. It's not an extremely good fit. It's a reasonable starting point. Okay, and then how could you go further? Well, again, this is a starting point. It gives us something to compare with. But a lot of times the Poisson is not good enough. And basically there's two major problems with the Poisson. Not necessarily for this example, but in general. Here's the two most common issues with the Poisson. One is in many data sets, there are a lot more zeros than you would actually expect from the Poisson. Okay? Because it could be that a lot of these women either can't have children or don't want to have children, and so that's just zero, you know, is necessarily zero, right? And so you could consider a model where and there are a lot of data sets like this, where if certain things can't happen and it's automatically a zero, and if it can happen, then use a Poisson, okay? So that's called a zero-inflated Poisson. And so that would be the next step up in complexity, right? It would be more work to estimate the parameters, right? It's a more complicated model. You would need to have more data in order to be able to estimate it well, because there's extra parameter. But the zero-inflated Poisson is saying, with some probability, just set it equal to 0. Okay, say probability p. With probability p, I'm going to say 0 children. Okay, and with probability 1 minus p, I'm going to generate a Poisson lambda. Okay, that would be a more flexible model, and that's useful in a lot of applications where you see, you know, you do a plot like this and you observe, hey, it looks a lot like there's too many zeros, right? The real data have too many zeros compared to what my model predicts. Okay, then you might want to try a zero-inflated Poisson. The other major limitation of the Poisson is that the variance equals the mean. And that's really simple. You know, that's a nice, convenient property. It makes things really easy to work with. It's easy to remember. But that's extremely restrictive, right? Do you really want to say that for any count data you look at, you want the variance to always equal the mean? That's not really realistic. And so in a lot of problems, it could go either direction, but it's especially common to find that the variance is higher than the mean in a lot of problems, where the data are more spread out than you would predict from the Poisson. And then a standard way to deal with that is to use what's called the negative binomial. Negative binomial distribution, it's one of the distributions we spend a lot of time on in Stat 110, and I'm not going to say much about it now, except that it's a natural extension of the Poisson. So if you take a Poisson lambda, and then you let lambda itself be random, that's going to give, in a certain way, that's going to give you a negative binomial. So it will generalize the Poisson. And the negative binomial, which we will probably come to later in the course when we get to the stuff about text analysis. But, you know, towards the end of the semester, we're going to be working with some text data, and the negative binomial is very, very handy there. It gives us an extra parameter to work with. So I'm suggesting, you know, start with simple models, compare them with reality, and then iterate, and you can build more complicated models, such as negative binomial. Okay. Here's the normal. I'm assuming you've seen it before, but you should definitely, if you're rusty on it, make sure you're very familiar with the normal distribution and its properties. The normal distribution is by far the most famous and most widely used distribution in all of statistics. You can see it's a symmetrical shape, right? It actually has various symmetry properties, which are very convenient. But in particular, the density is this symmetric bell-shaped curve. There are some numbers written in there that tell you how much area there is in different regions. So in particular, you see that 34.1% and 34.1%. So if you look at, and sigma is the standard deviation. So if you go one standard deviation to the left and one to the right, there's a 68% chance that a normal will be within one standard deviation of the mean. There's a 95% chance of it being within 2 standard deviations of the mean. And there's a 99.7% chance of it being within 3 standard deviations of the mean. That's a really handy rule of thumb to remember, and that is valid for all normal distributions. You know, it could be normal with mean 7 and variance 12. That's always going to be true. Those same numbers, 68, 95, 99.7. Okay, so why is this so important and so widely used? Well, remember I said that the exponential is characterized by the memoryless property? The normal has many characterizations. One of them is in terms of entropy. And I'm not going to give a precise definition of entropy, but entropy is kind of a concept about measuring randomness or disorder. And it turns out that the distribution for a given mean and variance, and if you want to maximize the entropy, which in some sense means you want to be as random as possible, that's going to be a normal distribution. So it maximizes entropy. That's one characterization it has. The most important characterization it has, though, is through the central limit theorem, which is an amazingly general theorem. It says if you add up a lot of independent random variables, it's going to look normal. Usually that's stated for independent, identically distributed. So for example, if you add up a Poisson of 1 and another Poisson of 1 and another Poisson of 1 and add up many, many Poissons of 1s, you're going to get something that looks normal, which kicks in very fast, actually. Like if you look at Poisson of 10 or Poisson of 20, it's discrete, but if you plot plot a histogram or the probability mass function, it'll already look like a normal distribution. So I just said the case where you add up Poisson of 1, Poisson of 1, Poisson of 1, Poisson of 1. Okay, but that will also work if you add up different distributions that are independent, adding up lots of things. Okay, that will generally work under great generality, and they don't even have to be independent, as long as they're not too dependent. Okay, so basically, you add up a lot of random variables, it's going to look normal. Except unless you deliberately contrive somehow to mess things up. Basically, how would you mess things up? It would be something where, like, I'm going to add up 1,000,000 different random variables, but I'm going to deliberately make one of them so extreme that it's going to dominate over the entire sum, right? So you're adding up many things, but you've somehow rigged it so that 1 or 2 terms dominate the entire sum. That might not look normal, okay? But under reasonable usual conditions they would encounter, add up a lot of stuff, it's going to look normal. So that explains a lot of the reason why the normal comes up over the place. Sometimes you don't want to add, though. Like is it reasonable to think that human heights are normal? Well, it's not really clear that your height is determined by adding up lots of little things. I might think that a multiplicative model makes more sense there, right? Like, certain things in the environment might increase your height by 0.1%, and then something else might decrease, height by 0.1% or things like that. So imagine many multiplicative factors. In that case, though, if you're working with a product, standard math trick is take the log. And by the way, that's also good data analysis advice. I heard it phrased this way once. If you have positive data and you're in doubt, take the log. That's not a theorem. That's handy advice. Okay? It's often the case that if you have positive data and you take the log, it becomes more normal or otherwise nicer to work with. And that's part of the data exploration process, right? You've got to make some plots, try some transformations, try to get a feel for the data. And what I'm just alluding to is what's called the log normal distribution. So if you multiply a lot of independent positive things, that's going to be approximately log normal. The log normal distribution is a distribution where if you take the log, you get a normal. So it should have been called log is normal, not log normal. And so for heights, log normal, human heights, log normal would probably make more sense than normal as your distribution. And in finance, log normals are used all over the place. When you're dealing with something with like a stock price, and this, stock price, it might go up 3% today, and then it might go down 5% tomorrow, right? So it's changing by certain percentages. The stock price is not going to go negative. It's a positive thing, and you're imagining kind of multiplicative things, right? Increasing by a certain percent, decreasing by a certain percent. Okay, so it would not make much sense to model stock prices as normal, but it would make a lot of sense to model them as log normal, and that was kind of behind the Black-Scholes equation, which revolutionized, and some people would say destroyed, the finance industry. So, lots of famous work in quantitative finance and in biology and, across the sciences is based on log normal distributions. Okay? To understand a log normal distribution, though, what you really need is to understand the normal. So just like I said, to get from an exponential to a Weibull, you raise it to a power. Right? I'm trying to show you some building blocks. Okay? Exponential is a building block you can use to get Weibull, and also gamma distributions and various other famous distributions are built on the exponential. And then from the normal, you can use the normal as a building block to get the chi-squared distribution. Probably a lot of you have heard of chi-squared tests and things like that, which I'm not going to review today, but chi-squareds are based on normals. Log normal, that I was just talking about, it's based on the normal. Okay? So normal is a building block for a lot of other distributions as well as being important in its own right for when you're dealing with sums. Okay, so in particular, they actually have these devices at the Museum of Science in Boston where, it drops balls and the balls can kind of go left and right in different ways. And you're showing visually or through simulation that the binomial is approximately normal under certain conditions. So if you have a binomial NP where P is not too close to 0 or 1, that is, P is reasonable. If P is 1/2 for the binomial, you're going to have a symmetric distribution, which is good if you're trying to approximate with a normal. The normal is always symmetric. Binomial, if P is not 1/2, is going to be skewed one way or the other. Okay? So the further that P is from 1/2, the more skewed it's going to be. If P is close to 1/2, though, it will be approximately symmetric. But if you now look at binomial NP and you let n get very, very, very large, and even if P is fairly far from 1/2, so it's very skewed, you're still going to get approximately a normal distribution. And the reason for that just follows from things that we talked about earlier today. In particular, I said that the best way to think of a binomial is that it's a sum of Bernoullis, right? So it's a sum of 0 and 1, 1 for success, 0 for failure. Okay? So if you have binomial NP and we think of it as a sum of n independent Bernoullis, and n is very large, that's just the central limit theorem. Right? Central limit theorem says that that's going to look normal. Okay. So that's a common approximation for binomial. All right. So central limit theorem is really useful because, one reason it's useful is that in statistics, often we're not necessarily looking at the sum per se, but we're looking at the average, what's called the sample mean of your data. Right? If you have a data set and you just take the average, right, add up the numbers, divide by the sample size, that's called the sample mean. Central limit theorem says if n is large, the sample mean is going to be approximately normal. And that's extremely useful because the true distribution of the data points may be some really complicated and unknown thing. You don't know how to work with that, right? And a common misconception in basic statistics classes is like, oh, why are we spending all this time on the normal when most data sets don't look normal? Okay? And that's true that for most variables, if you plot a histogram of that variable in practice, well, sometimes it looks normal, but most of the time it doesn't look very normal. But that doesn't mean that, your intro stat stuff is useless. First of all, we have that George Box quote, all models are wrong, but some models are useful. But more importantly, a lot of times we're looking at the sample mean. So the central limit theorem says even if the actual distribution of the data doesn't look normal, it still will be the case that the distribution of the sample mean will look normal. That's the central limit theorem. And this is what I call the magic of statistics, because, and this is one of the concepts, basically it's called sampling distribution, and students in intro stat, like Stat 100 type classes, usually struggle with that concept, but it's really fundamental. The idea is that the sample mean itself is a random variable. The sample mean itself has a distribution. The central limit theorem says that that distribution is approximately normal. And that's counterintuitive for most students at first, so I want to make sure you're all familiar with this concept. The reason most students have trouble with this at first is that you're just imagining you have one data set, because that's what you have, one data set, right? So you have one data set, you compute the mean for that data set, and then it just seems like that sample mean, which we usually call x bar, and then the students will say, well, x bar is just one number. It doesn't have a distribution, okay? But we're imagining, hypothetically, if you constructed many data sets from that distribution from that data generating distribution, imagine hypothetically many data sets, you compute the sample mean for each of those, and then you could plot a histogram of the values of that sample mean. So the sample mean itself has a distribution. Central limit theorem says it will always be approximately a normal distribution if your sample size is large. So the reason I call it the magic of statistics is, at first that seems impossible. Statistics is about, you're estimating, okay, it's not too surprising that you can estimate these unknown parameters. But the magic part is that you can not only estimate the unknown, you can estimate how good your estimate is, right? So you can say something about how uncertain you are about this thing that's completely uncertain, right? Which is kind of weird, right? Because you don't actually know. It's like you're measuring how well you're doing at approximating or estimating something when you don't actually know the truth. So it seems like it shouldn't be possible. But it is, under assumptions, okay? So in this case, what I was doing was assuming that the sample size is large enough such that the central limit theorem kicks in. And we can use the data to estimate the true mean and the true variance, and that will tell us what parameters to use for this normal, okay? So if we're using the sample mean to estimate the true mean, then we can come up with a confidence interval, for example, or different ways to quantify, how confident we are, right? We don't generally want to just say, here's our guess. We want to give some kind of uncertainty bounds that describe, how sure are we about that. Okay, so there's one way to quantify our uncertainty is through the central limit theorem. Central limit theorem is especially relevant when we're dealing with the sample mean, x bar, okay? But what if that's not what we're using for our estimate, right? What if we want to use the median or something like that? What if we're trying to estimate something different, okay? So far I've only been describing a pretty simple case where you're estimating the true mean using the sample mean, okay? But you might be trying to estimate something different. What can you do? Or it might be that you don't really believe that the data are very skewed, and you don't really believe that the sample size is large enough that the central limit theorem would make sense. Seems like you should be out of luck. This is the evil Cauchy distribution. I have a lot of distribution plushies in my office, by the way, if anyone wants to see them sometime. I just wanted to show this one. I just wanted to mention the Cauchy distribution because, again, a criticism, like, there was a famous book, The Black Swan, which basically, it had some good points in it, but it was basically making it sound like all statisticians are idiots because statisticians always use the normal distribution, which couldn't be further from the truth. Statisticians are very aware of many other distributions, and the normal, well, it follows from the central limit theorem, and it's a very convenient distribution, has a lot of nice properties. So we would use it as a starting point in a lot of problems, but it doesn't mean that statisticians think that the normal distribution always applies to everything. In particular, in a lot of real-world phenomena, you want the tails, right? Tails is out here in the distribution, to be heavier than you would get from the normal. And the Cauchy is a famous example of a distribution that has heavier tails. Turns out that the easiest way to define a Cauchy distribution is to take a ratio of two standard normal random variables. So if you take x over y, where x and y are independent standard normal, that's called a Cauchy. So again, the normal is the building block. You have to understand the normal really well first, and you can use the normal to create these heavier tail distributions. So for some applications, you want the tails to be heavier. Cauchy is much harder to work with than normal. It has much nastier properties, which is why they designed the plushie to look so unfriendly. It's okay, but you do have that option. And so, you have to iterate between, you want to do something that's simple enough that you can work with it, but not so simplistic that it's ridiculous. Okay. All right. So coming back to this magic of statistics, the last thing for today, I wanted to talk a little bit about the bootstrap. So we've reviewed the fact that if you're using sample mean as your estimator, then we have the central limit theorem available. We know it's going to be approximately normal. Normal distribution is very, very nice to work with. However, what if you're not using the sample mean, or what if you don't think the central limit theorem applies? Okay, so for example, maybe our estimator, maybe we're trying to estimate the median of the distribution of interest. Median means half of the mass is to the left and half of the mass is to the right. Okay? We want to estimate the median, and a natural way to do that would be take your data set and then pick the median. The median just means you sort the numbers and pick the one in the middle. And if there's two in the middle, because you have an even number, just average those. Okay? So maybe that's called the sample median. So maybe we're using the sample median to estimate the true median. Well, there are theorems that do say that the sample median will be approximately normal as well. But that's, in general, the median is going to be a lot harder to deal with than the mean. Sample median is more complicated than the sample mean. Because for the sample mean, for example, we can use things like linearity, right? If we want the expected value of the sample mean, it's a sum, right? So we know how to deal with sums. Medians are more complicated than means, and sample median is more complicated than sample mean. And we could be doing something more complicated than that. So we don't have central limit theorem. We don't know what's going on. All right, but there's an amazingly general idea that we can still quantify our uncertainty, and that's called the bootstrap, which was invented by Brad Efron in 1979. Efron is one of the greatest living statisticians, and he's done a lot of work, but the bootstrap is his most famous contribution. So the idea is like this. We have some data set here. I just made up some numbers. These are actually, that looks like pi and e and square root of 2 and log of 2. So actually, those are not random numbers, but suppose that's our data set right there. And then we have some estimator, right? Maybe we calculate the median here, which would mean I would just sort these numbers and pick the one in the middle, or whatever estimator we come up with, right? An estimator could be any function that we calculate from this data, right? That's also called a statistic. Statistics is the study of statistics. A statistic just means anything you can calculate based on your data, right? You have some data, you calculate something, that's your statistic. Okay, so you can calculate that thing, but once you move to estimators that are more complicated than just the sample mean, the math usually gets really intractable. Like, how do you find the standard deviation of the estimator? So in other words, what can you say about how close you think your estimator will be to the truth? Things like that. Sounds like an impossible problem, but Bootstrap, it sounds like an impossible problem because, as I was mentioning earlier, when I was talking about sampling distributions, the fundamental problem is that we only have one data set, right? We wish that we had many data sets and we could calculate our estimator on each of them and plot a histogram of the values of that estimator, right? But then the reality kicks in, we only have one estimator. What can we do? Sounds hopeless. Bootstrap says, let's make up some fake data sets, okay? So it really seems too good to be true, and in some cases it is. This is not a panacea. There are no panaceas in statistics. So this is not always going to work. But it's amazing to me how often this does work well, even for fairly small data sets. Maybe not with 5. I just did 5 here because I didn't want, to write a big data set up there. But, even with 10 or 15 elements, it's often quite good. So what do? We want a new data set, and we want lots of them, and we only have one. And suppose we can't actually go out and collect more. Ideally, you would go out and collect more real data, okay? But suppose you're just sitting at home and you can't really go out and get more data. What do? Make up some fake data. How do you do that? Well, Bootstrap. Bootstrap means what you do is you resample. It's a resampling technique. You resample from the data set you have, because that's the only data you have, with replacement. Okay, so notice there I got 0.693 twice. Okay, so I picked 1.414, 2.718. I'm just picking 2.718 came up twice. Just drawing from those with replacement. So pick one, put it back. Pick one, put it back. Okay, and then do it again and again and again. It's like 2 lines of code, and run it for 1 second, and you can generate as many of these as you want, right? It's extremely easy both to code it and to think about it. What is it doing? It's just generating fake data sets using the same values with replacement. Okay, well, the first time I saw that, I thought it was completely ridiculous, because you're not getting any new data. And also, you're introducing all these repetitions. So if the original data are continuous, there's never going to be repeated values. But here you're resampling with replacement, so you're going to get a lot of duplicate numbers. And you only have this pool of 5 values, and you just keep resampling these. How is that useful? What does that actually tell you? Turns out there's actually tons of math now on the Bootstrap. There's thousands and thousands of pages of hard theorems about it, showing when does it work and when does it not work. But it works an amazing amount of the time. So let me just describe in a little bit more detail the intuition and a little bit more detail about how do you actually use it. Okay, so Bootstrap means you generate these replications. They're fake data sets that we call our replications. And you could generate, say, 1,000 of them in a second. Now you have 1,000 fake data sets and 1 real data set. And then the idea is, if you're studying, say, sample mean or sample median, you compute for each of those fake data sets, you calculate the estimator you're interested in, pretending that was the real data set, right? So you could calculate, if you're doing sample median, you could calculate the sample median for each of those things, okay? Calculate all those sample medians, and then plot a histogram of them, okay? And so you would basically approximate the uncertainty in your sample median by what it looks like in that histogram of values from the bootstrapped data sets. Okay? So that's why it's called, there's a saying about pulling yourself up by the bootstraps. That's where the name comes from. It sounds like you're getting something for nothing. And there's a picture here that explains a little bit more about what it's doing. So over on the left, that's the real world. In the real world, we face the following problems. First of all, we're working with a model, and a model, as we said earlier today, a model is a family of distributions. We don't know which of those distributions is the true one. So we have an unknown true distribution, and we only have 1 random sample, right? We have 1 data set. Okay, and then we're interested in calculating a certain statistic that we're using to estimate something. And over on the right is the Bootstrap world. Bootstrap world is designed to mirror the real world. But the beauty of the Bootstrap world is what distribution you're working with. The distribution you're working with in the Bootstrap world is what's called the empirical distribution. The empirical distribution is what the name suggests. It's the actual distribution from those data points that you have. So like, if you suppose you have a sample size of 10, and consider the distribution that puts probability 1/10 on each of those 10 points. that's called the empirical distribution, okay? And when you're generating these bootstrap replications, what you're really doing is just sampling from the empirical distribution, right? Because you're just reusing or recycling those same values over and over again. The beauty of this is you know the empirical distribution. That's why it's empirical. And so then you can generate as many bootstrap samples as you want, 1,000 of them, you know, in less than a second. And then you basically just take everything that you want to be doing in the real world and you mimic it in the bootstrap world. And the theoretical, there's tons of math about this that we're obviously not going to get into, but a very quick way to describe why this is at least plausible is that there's a theorem that says that the empirical distribution will always converge to the true distribution as the sample size grows. And that actually follows from the law of large numbers. Law of large numbers says that if you take the sample mean of, sample mean for any distribution, it's going to converge to the true mean. That's just saying as you get more and more data, you should be able to get closer and closer to the truth. So if your data set is large, the empirical distribution is going to approximately be the same as the true distribution. And then the bootstrap world actually is close to the real world. So there's tons more theory behind it that we won't get into, but that's kind of the rough idea, is that you're working with the empirical distribution. And this was kind of ushered in the era of computer-intensive statistics. And part of Efron's motivation is try to find methods where we let the computer do most of the work. Instead of doing incredibly hard, long mathematical calculations, this is just something you can do yourself on the computer. Computer does the work for you. So it's extremely useful. All right, so I'm going to stop here. Good luck with the homework.